So this is what we have done so far. That is, as you can see, the title of this lecture is the further concepts in wave mechanics. So one thing is clear that a Schrodinger equation for a non-relativistic particle moving in one dimension is given by iota h ket del psi upon del t is equal to minus h ket square upon twice m del square upon del x square plus vx into psi x. And this psi x uh, happens to represent the state of quantum system, whether a single particle or a system of particles. Uh, and this what are some conditions? What you can say? What are some physically acceptable conditions? Phys what are some conditions that this remains physically acceptable solution? The one of them is that this psi x must be single valued. In general, it is a complex valued function, but it should be a single valued function. Okay, it should be continuous. The Since the second order derivative and the first order derivative are defined, one thinks that if second order derivative is defined, then the first order derivative must be continuous. Indeed, it happens for the most of the cases, but for few cases, for few trivial cases, you'll find that this d psi upon dx will not remain continuous at some points. We'll do those cases. And such solutions in mathematics are called as the weak solutions. Okay. So for example, if I'm saying that the second order derivative exists, so one is tempted to think that, okay, the first order derivative must be continuous, because after all, here you can see that there is a second order derivative in time, in space, in coordinate. So one thinks that, okay, since second order derivative is defined, then it should imply that the first order derivative must be continuous. But it happens so that this first order derivative is not continuous at some points in some potentials. For example, this is one of those potential, one of those trivial cases. We'll discuss all these things in detail as we are going to take up the potential problems. But right now, on general, I can say that d psi by dx is not continuous. Okay, it's not continuous in general. Okay, so there will be cases where d psi by dx will become discontinuous at some points, and despite it is discontinuous at those points, still the second order derivative is well defined. Okay, so again, I'm saying such solutions are called as the weak solutions in mathematics, and they do exist. So don't worry about them. Okay, now further as I go, we should also make a point very much clear that psi must be squarely integral. And when I'm going to talk about all these things in Hilbert space, I'm going to use certain notation for them. That is L square. This is how you write the space of squarely integrable function from A to B. All those notations and mathematically rigorous things we are going to do in a linear algebra thing. But right now, let us focus on more on the physics side. So one thing is clear that psi mod whole square dx, this particular thing from minus infinity to infinity represents the probability of finding the particle somewhere in the space from minus infinity to plus infinity. So clearly, since it represents probability, it should be some real value. I mean, it should have some real value. And since it should have some real finite value, it cannot diverge, because if it diverges, then this particular sense does not make, I mean, this particular thing does not make any sense. So this is one thing that you should know. Now, as I go, let us do a few questions and understand that whether or not this particular form, that is a secant of x, does it form a physically acceptable wave function? Does it form a physically acceptable wave function? So I hope everybody understands that this does not form a physically acceptable wave function, because it becomes infinite as x tends to, or as x is equals to pi by 2. So clearly one knows that the secant x would tend to infinity as x is equals to pi by 2. Similarly, one can say that, okay, a tangent of x will also not form a physically acceptable wave function, because as x tends to pi by 2, a tan x would go towards infinity. In fact, it is also discontinuous at x equal to pi by 2. So if you are aware of the graph, you can see that if I make the graph of tangent, so it will go from here to here, and at x equals to pi by 2 to the left hand, it will go towards infinity, and to the right hand, it will go towards minus infinity. So you know that a tangent of x can also not become a physically acceptable wave function. And the same way you can think of this thing. Let's say if I give you an example of e to the power x squared, not minus. So you know that as x tends to infinity, x tends to plus minus infinity, a e की power of x square would go towards infinity. So for a physically accepted wave function, this is already reprimanded to us that psi must go towards 0 as x tends to plus minus infinity. This is the condition. These are the condition for physically acceptable solutions. Okay, so one has to remember them. Okay, so these are okay. So one has to understand that a e की power x square cannot form a physically acceptable wave function. No doubt, a e की power minus x square would indeed form a physically realizable wave function. And one can know that one knows from previous experience, and we've also done a class on Gaussian curve sketching, and we know that the curve is very much clear, and it's quite useful in your statistical mechanics and all the other places you'll find that this Gaussian will come into the frame. And we know that as x tends to infinity, this particular fellow goes towards 0. Obviously, this is bounded, that it is continuous everywhere, or it is differentiable also everywhere. In fact, the derivative is also continuous everywhere, and that it is quietly integrable as well. What is after all, see, what after all represents your what after all represents psi mod whole square dx? It represents the probability of finding the particle somewhere in the space if I integrate from minus infinity to plus infinity. So one can say that actually it represents the area. And since we know that this is a bounded function and continuous, so it is Riemann integrable function, and the area would be something. The area would be something here. So area is well defined. So one can say that this particular thing would be well defined. Or you can say this particular thing will be some finite value. So indeed, this psi x is a square integrable function, and you can use it. Uh, as a physically acceptable wave function. So indeed, it is a square integral. Okay. Now we have already done a few things, but today a few new people have joined. So let me help myself with some important things that we've already done. Okay, so this is last time that I'm doing the same, but next time I'm going to see what is my objective of this course is. I want to teach from students from the JAM level to NET level. So, for example, if somebody is at BSc level, he also should get a few of these things. So that is my objective. As I told you that according to Bond, the psi mod whole square represents what? It represents the. Just give me a minute. Okay, so this represents the psi mod whole square according to Bond represents the probability density. Now, when it comes to probability density, one would be tempted to ask in what sense. So let's say in length sense or in volume sense, it depends upon how your wave functions. So for example, if your wave function is defined as a function of x and t, that is in linear one dimension, then this probability density, you can say that it is a probability density of finding the particle between x and x plus dx. And if I integrate this stuff, let us say from A to B, it will represent the probability of finding the particle from A to B. Okay. Now understand that this psi x, this particular psi, which satisfies this Schrodinger equation, one can clearly identify, and if one is aware of a linear differential equation, one can clearly see that if this particular fellow is linear in psi, so this particular differential equation, you can see this is a linear differential equation. Okay, so one can say that this if psi is a solution, then A times psi is also a solution. So I can write if psi is a solution, then A times psi is also a solution to the Schrodinger equation. Okay, is also solution. So and this particular A is referred to as the normalization constant. Normalization constant. And how it is found, these are very basic things, but still okay, so what does psi signify? See, psi in general does not have any physical relevance. Okay, psi does not have any physical relevance as such, but okay, it is a mathematical way of representing a particle in space. Okay, so let's say when we are talking of what should I say? When we are talking of classical mechanics, uh, every particle, let's say any particle in phase space. So when we are talking of classical mechanics, the fate of the particle or the fate of the system is completely governed by, you can say, uh, uh, by saying x and p. So let's say if I give you a position and if I give you a momentum, you'll be able to determine the fate of the particle. Let us say I tell you that this is your particle, and you don't give it any velocity and just leave it on its. So you understand that it is going to execute a free fall. And given any time, you can say that, okay, the position of particle would be something like xt is equal to ut plus half gt square or something this way. Okay, so you can with all determination you can find this x, and obviously you can find the momentum at any stage of time. Let's say if you don't give the velocity here, you give the velocity in the horizontal direction. You know from your standard 11 that this is going to execute a parabolic trajectory, and you give me a time and I'll give you the value of x and I'll give you the value of p. In fact, if you give a velocity which is greater than probably, let's say you give a velocity of orbital, let's say, what is that called? Orbital velocity, it is going to execute some elliptical motion around the Earth itself. So you know the trajectory of the particle, you know the position, you know the momentum, you know everything. I mean, you know both of these things with all determinism. You give it a velocity greater than the escape velocity, it is going to deviate through hyperbolic trajectory and would never come back. But still, you can understand that at what time, where it would be. So understand in Newtonian mechanics, or you can say in general classical mechanics, there is a sense of determinism. When it comes to quantum mechanics, there is not a sense of determinism. So if I'm saying a particle is here, you don't know particle is here or not. Okay, so basically there is a lack of sense of determinism, because uh, in general quantum mechanics is governed by the uncertainty. So there is an uncertainty in determining the position and you can say what you can say in determining the position and momentum simultaneously. So therefore we don't use this kind of construct here. We don't use this kind of construct. So further, we also understand from development of quantum mechanics that a particle in space is represented by, it can be represented by wave function. That is, you can, we are going to consider this. I mean, we are going to discuss all these things in greater detail, like wave packets. But what we think that, okay, if this is a particle, how to represent it? So we represent it as a wave packet of many waves of different amplitudes, of different you can say wave numbers or wavelengths, and we take this superposition in a way that it interferes constructively in a localized space, and beyond that it interferes destructively, so that you can think of it being confined in a space. So since it is a confinement, you cannot talk that whether your particle is here, whether your particle is here, whether your particle is here. This kind of stuff, mathematically, we represent it using psi. So this is what you can take at best, you can say at best what you can say about psi. Okay, but the physical, you can say interpretation for this is that psi mod bool square represent the probability of finding the particle somewhere. Okay, it represents the probability density. So basically, if you are thinking about this, I'll come to all these things in wave packet formalism. But right now, just think that in general, you don't represent particle with all determination. So what you do, you basically consider it as some superposition of waves. And as I told you, it is done in a manner that it interferes constructively in a space and interferes destructively beyond this. So basically here the probability of finding the particle is zero, but here there's some finite probability. But again, probability. It's not, we are not very sure that whether particle is here or somewhere. So basically, this is a mathematical construct. You can say this is a mathematical construct to represent quantum particle in quantum particle in quantum mechanics in center. You can right now you can take this way. There is a great amount of rigorous theory behind this, and I'll come to that. And probably I'll need a lecture on Fourier transform, and then you'll be able to understand what I'm saying. But right now, just take it as a like I'm saying mathematical construct to represent a particle in quantum mechanics. You can say, okay, or you can say in general a state in quantum mechanics. Deepta, is that clear or not clear? I mean, right now you can take this much of input. Okay, is that clear or not? Okay, okay. Because see, this particular formalism I'm going to demonstrate. Don't worry about it. But right now, just consider this little bit of consideration you'll have to make. So psi x is a mathematical construct which contains all the information about the state of the system. And all these things will look to you very difficult at start, but let us make it of let us first understand all these things mathematically, and then we are going to then these things are going to make some sense later on. Okay, so one thing is very much clear that if I use this condition that psi mod whole square, and you know that what is the condition for certainty and probability? If I say that the event is certain, then the probability must be 1. So indeed, this gives us the condition that from minus infinity to plus infinity psi mod whole square dx, or let's say if it is in 3 dimensions, then it would be d tau. You can say all space here, right? Rather, this should be equal to 1, because probability would be something, right? If I'm saying that particle is somewhere in the space, so it is a certain event, right? In that sense, means somewhere I have to find. So this particular thing should be unity. If I use this condition, I'll be able to find this A, and this A is called as a normalization constant. Now, this brings us to a very important question, that whether or not this probability is conserved. So one of the important questions is that whether this probability density, I would say rather, probability density is conserved or not. And this is very necessary also. Why? Because see, if I say that my probability density is not conserved, then how would I be able to make the assessment of A? Because let's say I normalized my wave function psi at t equal to 0. And if probability density is not conserved, or let's say if probability is not conserved, then this will evolve in time. And if it evolves in time, what will happen? If I'm making let's say if I'm finding A at some time t equal to 0, then my normalization should change with time, because this is also evolving in time. And we understand that if in order to find A, what is the thing that we are doing? We are trying to say that psi mod whole square integration is equal to some constant. Okay, so one has to understand that this particular thing remains conserved. This particular thing, this probability remains conserved. Is that clear? I'll demonstrate it, don't worry. But understand this point. Is that clear or not clear? Who all are attending the class? So, Alpna, is that clear or not clear?
नहीं भैया एक बार और please.
Okay, so what I want to say, see, if I'm making a sense, if I'm saying this thing, let's say if I'm saying that psi, if psi is a solution, then indeed A times psi is also solution, right? Because psi is a linear in. So, for example, whenever you consider linear differential equation, if psi is a solution for that particular differential equation, then A psi automatically becomes a solution. This is this is you can say this is one of the properties of linear differential equation. This A, when we talk in physics, happens to be the normalization constant. Okay. Now, what I'm making sense is that if I'm saying that this represents probability of finding a particle. Okay. Probability of finding the particle somewhere in the space should be unity, right? It should be somewhere in the space. If I'm saying that psi represents in abstract, let's say particle, mathematically, if I'm saying that, let's say it represents some state, or let's say it represents some particle in space in general, in quantum mechanics, then this psi mod whole square dx should give me unity. Okay, I'm certain that okay, somewhere in the space it should be there. This is one thing. And if I want to find A, what I'm going to do, I'm going to use this condition only. So instead of psi mod whole square, I'll use A. And what is psi mod whole square? It is psi star. So basically it will become A star A, and I'll use this condition. And from here, I'll be able to extract this A mod whole square. Because I know that this particular thing is equal to 1. So if this is not conserved in time, if this is not conserved in time, it keeps on changing, then this particular fellow also keeps on changing. So one has to remember that this particular thing remains conserved in time. So there is a conservation of probability with respect to time. I mean, this is something that I've taught, but let's say today a new child has come, so let us redo it. So conservation of probability. So see, let us understand this particular thing. So if I'm saying, okay, one more thing you should remember, psi in general is a function of x and t, and it is governed by, you can say, Schrodinger equation. Okay, so this is one thing. And let's say if I'm saying, I want to know that whether my probability remains conserved or not, whether my probability remains conserved or not. So mathematically, how should I represent? What is the conservation? So I'm saying that whether my probability remains conserved with respect to time or not. Okay. So if it remains conserved with respect to time, obviously then A should also remain constant. But if this fellow keeps on changing with respect to time, then this particular fellow also keeps on changing with respect to time. So question arises that if I'm normalizing my wave function at time t equal to 0, if I'm normalizing my function at time t equal to 0, does it necessarily imply that it remains conserved forever? So the point is that if at all this happens to be a function of time, then what will happen? At t equal to 0, you normalize your wave function, but at a certain later time, because this evolves in, if it evolves in time, then this also should evolve in time. So you'll have to find another normalization constant at a different time. But luckily, it does not happen to be the case. And somehow, one of the very crucial features of, you can say, Schrodinger equation is that this preserves the normalization of the wave function. So I'll write it here. So one of the interesting features of Schrodinger equation is that it preserves the, you can say, normalization of wave function. So this is something it does. Now, one is tempted to ask that how do you say that? So let us do that first. So let's what it is equal to, and I hope everybody understands that this is in general a complex valued function, and this should be given. It is given by psi star psi dx. And you should remember that when I'm saying that it is psi is a function of time and space both. So if I am making a total derivative outside, if I want to take a derivative inside, this is a Leibniz rule. When I take a derivative inside, since psi is a function of x and t, I will resort to the partial derivative. I cannot take a total derivative when it comes inside because psi in general is a function of both x and t. So if I'm making some sense, I think this would be equals to minus infinity to plus infinity psi mod whole square dx. And then you have this minus infinity to plus infinity. I'll take this del by del t inside. And then I have this psi star and then this psi dx. And what will happen? I'll write it this way. This I'll write somewhere here. So del by del t of psi mod whole square would be equals to what? It will be equals to, I should write psi star and then del psi upon del t plus you can say del psi star del t and psi. So this I'm going to replace it here. And we understand that this psi after all is going to satisfy the Schrodinger equation. So I'm going to put this here divided by iota h ket. This is something that you can do on your own, but I'm going to write directly that iota h ket upon twice m, and then this is del square psi upon del x square, and then minus iota upon h ket, and then you have this v, and then you have c. And del psi star upon del t would be minus iota h ket upon twice m iota h ket, and then you have this v psi star. Okay. Okay. So if I use both of these fellows here, and if I multiply with psi star this thing, and if I multiply with psi this thing, what you are going to get? So let's say this is probability with respect to time. I'm writing it this way. And from minus infinite to plus infinite, okay. So if I'm differentiating with respect to time, minus infinite to plus infinite, this is what it is going to be. So this is psi star into d psi by dt. It is going to give me iota h ket upon twice m, and then uh, inside I'm going to take this. So inside this would be psi star del square psi upon del x square, and then it would be minus of, if I'm, and this particular fellow and this particular fellow will vanish. You can see on your own. Because this is an addition sign, this and this would get cancelled, but only these two things remain. And you another thing you will get del square psi upon del x square into, sorry, this is I think psi star. Psi star is here, and then you get psi here. And this is what I have done. Okay, this is one thing. Okay, and now if I integrate this thing, so I'll get iota h ket upon
हेलो
twice m.
सर
हाँ बेटा.
सर वो जो इंटीग्रेशन के बाद जो डीडीटी है मतलब वो होगा क्या मतलब वो तो पहले ही हम तो उसका मतलब
I'm so sorry.
हाँ सर
I'm so sorry. Okay, so iota h ket del iota h ket upon twice m, and then you can integrate this thing, this particular thing. So what should I write? I will write one thing. I will say that this particular thing from minus infinite to plus infinite, this is del by del x, and then you have this. What should I write? I should write it as uh, so. So this is equivalent to writing del by del x of, just give me a minute. I think this will be it. Equal to इसको सोचते हैं थोड़ा सा, minus okay. So if you differentiate it, just try to differentiate. If you differentiate, you get del psi star upon del x, del psi upon del x minus del psi star del x, and del psi upon del x. This would get cancelled. You keep this here as it is, and then you differentiate. So del square del 2 psi upon del square x, this would come, and this would come. So basically, writing this and writing this is same. So d by dt of probability as a function of time, that is minus infinite to plus infinite psi mod whole square d. What is that? Dx is equals to what? It is equivalent to writing this. And if I integrate with respect to time, what am I going to get? Integrate with respect to x. So this thing, but this particular thing, I'll get psi star. Then I'll get del psi upon del x minus del psi star del x, and then psi from minus infinite to plus infinite. If I place plus infinite here, I understand that this particular fellow is going to 0, this particular fellow is going to 0, because we understand that psi x, as x tends to infinity, my psi must go towards 0. So if I take both of these limits, this will give me 0. What does it imply? It implies that the probability remains conserved with respect to time. So I'll write that probability remains conserved with respect to time. And if psi is normalized at t equal to 0, then it remains normalized at all future times. Okay, then it remains normalized at all future times. The same thing, you can also think when it, I should write it here. So for example, if you have two solutions to, let us say two normalized, I'll say, write it here. Let's say, for example, when we are going to study a little bit further, we're going to see that depending upon what cases you are doing, let's say you are doing one-dimensional, you can say infinite potential field. So the wave function can be there. You find that there are the wave function can be represented as superposition of various orthonormal wave function. So there are probabilities. There are the probabilities associated with all those wave function. So if I say that, let's say I have two wave functions. So let's say psi1 and psi2 are two normalizable you can say wave functions, or you can say solutions. Solution to the Schrodinger equation. Okay, then also you'll find that this d by dt of minus infinity to plus infinity psi 1 star psi 2 dx, this also remains to be equivalent to 0. So we have seen that if I just take both of them equal, that is, if I take psi 1, psi 2 both equal, then it will represent psi 1 mod whole square, which is probability of finding the particle, for probability of finding this thing as particle governed by wave function psi 1, psi 1. So for example, if I write psi 1 equal to psi 2, then it will be simply the same case that we have already done. Now here I have taken a different case. I have written that if these two are normalizable wave function to a Schrodinger equation, then also this particular mathematical construct, that is psi 1 star psi 2 dx, obviously it is not going to have any sort of you can say physical representation, but it represent later on when we are going to see, it represents an inner product of psi 1 psi 2. So all these things you are going to see later on, but right now just consider that this particular thing, that is d by dt from minus infinity to plus infinity, psi 1 star psi 2 dx will also be 0. I think I should little bit tell you about this, and then we're going to see one very important and interesting case. So just don't lose keep little bit of motivation here. So so d by dt of minus infinite to plus infinite, if I write again, as I told you, if I, since psi is a function of both time and space, so if I'm doing d by dt, if I want to place it inside, I will have to do a partial derivative, because understand that after all, this psi is function of both x and t. I cannot take this total derivative completely inside. And this is also referred to as Leibniz rule of differentiating under integral sign. So this is quite technical. This is acceptable, so don't worry about the mathematical acceptance for the same. So psi 1 star psi 2 dx. Okay, and what it will lead us to, it will lead us to minus infinity to plus infinity, and then you will have del psi 1 star, and then you will have del t, and then you will have this fellow, that is psi 2. Then again you will have this psi 1 star, and then I'll write this is simply product rule, nothing else. Okay, and we already understand from the equation given above that del psi star, or let's say del psi upon del t, is iota h ket upon twice m. So instead of psi, I will use psi 1 and psi 2. Okay, this equation I'm going to use it here instead of this and this. So let us use and see what happens. So if I use it here, so what will happen? Minus infinity to plus infinity, del psi 1 star upon del psi, del by del t of psi 1 star, what it will be equals to? It will be equals to, I will write it here, minus iota h ket upon twice m, and then you will have this del square psi 1 upon del x square plus iota upon h ket v psi 1 star, and then multiply, in multiplication we'll have psi 2 plus minus, and then this dx, fine, minus infinity to plus infinity. This is psi 1 star, and then you have this iota h ket upon twice m del square psi upon psi 2, sorry, up upon del x square minus iota upon h ket v psi 2 dx. I hope it is clear till now. And if I try to see this psi 1 star, and this is psi 2, this psi 1 star, this is psi 2, this is iota h ket upon v, this is minus iota h ket upon v. If I add them up, clearly this particular thing would get cancelled, and I'll be left with only these two terms. Okay, so I'm using these two terms in so I'll take this also outside. So let's say I'm taking minus iota h ket upon twice m also outside. So if I take this outside, what am I going to get? I'm going to get del square psi 1 upon del x square psi 2 minus of psi 1 star del square psi 2 upon del x square, all being integrated with respect to x. Okay, all being integrated with respect to x. Now, if you find this particular thing, what are you going to get? You're going to get, now let us integrate this. Okay, so let us integrate.
होगा ना वो
हाँ जी बेटा,
वो इंटीग्रेशन के अंदर जो साइन है माइनस होगा मतलब प्लस होगा ना, मतलब हाँ माइनस आई स्क्वायर बाई 2m कॉमन ले रहा है।
देखो माइनस आयोटा एच के अपॉन पाई से हम कॉमन ले रहे हो, सो ये पहला वाला तो माइनस, यहाँ पर क्या है बेटा प्लस, सो एक क्या नेगेटिव, ये तो प्लस ही ना यहाँ पे, सो यहाँ एक नेगेटिव एक्स्ट्रा आएगा।
ओह सॉरी 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 सर, ठीक है।
ओके, कोई इशू नहीं। तो अभी व्हाट आई विल डू, what I'm going to do is I'm going to integrate this. I'm going to integrate this by parts. Okay, so I'm going to integrate it by parts. Uh, so let us do that. So first, if I'm integrating the second derivative, what it is going to yield me? It is going to yield me the first derivative. There is something wrong here, I think. Acha, this is Simon star. So Simon star should come. Okay, my mistake. Okay, Simon star should. Okay, because see, here we had this thing now. अभी देखो it is del by del t Simon star. So here you will have this is from this. Okay, this is from this. Okay, so don't worry about all these things. So now what I'll do, so this is a little bit complicated, but let's do it. Okay, let's do it anyhow. So if I integrate this, see, it is easier to integrate this now. So I'll integrate this. So you know now, integration by parts, you know now. So if we have to select one integrable function and other as a differentiable function. So one integrable function is this, another function will keep it as a derivative differentiable function. So now let us integrate. If I integrate this thing, I'll get del psi upon del x. Psi1, sorry. Psi2 will remain as it is from minus infinity to plus infinity. Minus infinity to plus infinity. This derivative, this is integration by parts, by the way. It's integration. This integration would give me del psi1 star del x dx minus of psi1 star integration for this particular thing, del psi2 upon del x from minus infinity to plus infinity. And then since this is a negative, understand in by parts there is again negative inside, and then this negative will give me positive. Minus infinity to plus infinity, this will give me, I have to take the derivative for this thing, del psi1 star del x, and then you will have del, its integration. So I think because of the lack of space, I think you will be able to do it on your own. Okay, so just confirm on your own. This would be the case. Now just think about these two fellows. This integration and this integration would get cancelled. At plus infinity, this would go to 0. At minus infinity, this would go to 0 by the condition for the physical realizability. At plus infinity, this would go to 0. At minus infinity, this particular thing would go to 0. And you are going to get an answer as 0 here. So one can also extend the same thing that I did previously for psi mod whole square. I can extend it for even two physically acceptable wave functions which are normalizable. So for example, if psi1 and psi2 are normalizable solutions to the Schrodinger equation, then also this particular thing, that is the derivative d by dt minus infinity to plus infinity, psi1 star psi2 dx is equals to 0. Is that clear or not clear? Please let me know. Okay, so okay, now you see one of the interesting features that you're going to see here is that when I was resolving this case for you, one thing was very much clear, that I was taking potential function to be the real function. See here, everywhere in the above thing that we have discussed, we have taken potential to be real real function, potential to be real function. Is that clear or not? See, if I see here, this particular, where it has gone, just give me a minute. Okay, so here, if you see, I have taken V to be real, because if I take V real, only then I'm not making any star here. I'm not taking conjugate. So when I was taking conjugate, I was not taking conjugate of this particular thing, because if V is real, taking conjugate does not make any sense. Okay. Is that clear or not? Yes or no? Please let me know. What are you getting my point or not getting my point? So what I'm trying to make a point is that in this discussion, I was taking V to be real. Yes or no? Deepta is there or not there? Okay. Somewhere.
Yes, sir.
Okay, good. So I took V to be real all through. Now question arises, what if V is not real? What if V is not real? So one of the most bolder statement I'm going to put forth is that if V is not real, then your probability is not going to remain conserved. If V is not real, then the probability is not going to remain conserved. So for probability to remain conserved, the first condition, no doubt, is the solution for the Schrodinger equation. Psi must be a solution for solution of this Schrodinger equation. This is fine. This is the obvious. But understand, we when we were doing this thing, we were able to cut this V, because V was, after all, a real function. Because if V is a real function, then I will not place a V star here. What if V is not real? What if V is not real and it is accompanied by some complex counterpart? So you'll find that then your probability is not going to remain conserved. So this is one of the things that can be asked in your interviews or exam anyway. So this is something that I'm going to write, and I'm going to prove it also. Don't worry about it. So let us say, I'll take an example and make you understand this thing. So let us take an example of an unstable particle. You understand that an unstable particle will disintegrate in as a function of time. So many of you people are aware of, let's say, alpha decay, beta decay, or any nuclear decays. So one understands that particle there decays, or you can say has certain lifetime in which it disintegrates. So let us consider the case of an unstable particle. Consider the case of an unstable particle, and which spontaneously disintegrates, with a lifetime tau. Okay, so clearly now you see that now it's disintegrating with respect to time. Okay, so now we can no longer say that probability is constant here, because now probability will become a function of time, because now particle is not only particle, it also evolves with time. So basically now probability no longer remains a constant. Okay, and in fact you'll find that in these scenarios probability varies exponentially as a function of time. And this is something that I'm going to do, don't worry. So no longer it remains conserved. So one thing is this, and second thing, please do remember, when I was doing your case, one has to understand that if V is real, then d by dt minus infinity to plus infinity psi mod whole square dx is equals to 0. But what if V is not real? What if V is not real? And this is something you can relate. See, understand, when I'm discussing unstable particle, I'm saying that this node, it is a particle, no doubt, but it disintegrates with respect to time. So it basically evolves with respect to time. So its wave function will be indeed, you can say that if I want to take the derivative with respect to time, and this particular fellow also evolves with respect to time, how can I say that in the case of unstable particle, probability remains a constant? So it no longer remains a constant. Further, for such cases, the potential will not be real, rather it will be non-real, because you know that if V is real, then probability cannot vary. it will be constant. But what if V is not real? What if V is not real means, what if I say that that V has some imaginary part as well. So if V has some imaginary part as well, then what happens? So this is something that I'll do it for you. So for example, let's say now your potential is no longer your V, rather it changes to some V naught, which is real part, minus iota gamma, which is, let's say, some imaginary part. So now no longer your what you can say, no longer your potential remains real, rather it is accompanied by a imaginary part as well. So this is your imaginary part. Now question arises that if this is the scenario, does probability remains conserved? Does probability remains conserved? This is one of the questions that we are going to address. Okay, so one should be very much clear that after all, the psi is in any case it is going to satisfy the Schrodinger equation. That is very much clear. That is not going to change. But now because of V, things would certainly change. Now because since V is now imaginary, things would change, and let us see how it would change. Okay, so we understand that we've written that the psi satisfies Schrodinger equation. So I'll write my this is iota h ket upon twice m del square psi upon del x square minus iota upon h ket v psi. Now understand, now V is no longer your V real, rather it is V naught minus iota gamma. So what will happen? Now I'll have to do conjugate. So I'll take a conjugate part. So it is going to give me minus iota h ket upon twice m del square psi star upon del x square plus iota h ket, now V star and then psi star. Okay, and we understand what is our del by del t of psi mod whole square. Del by del t of psi mod whole square is what you can say, del by del t of psi mod whole square is given by del by del t of psi star psi, and which is actually equals to psi star del psi upon del t plus del psi star del t times psi. So if I use this, what am I going to get? So that is what I have to use it here. I'll use it here. So I'll use it here. So my del by del t of psi mod whole square would be equals to what? Psi star into del psi upon del t. So psi star, if I multiply by del psi upon del t, so it will give me iota h ket upon twice m. You will have a psi star here and del square psi upon del x square minus iota upon h ket v psi mod whole square, because psi star into psi is psi mod whole square, plus this thing, this would be, I think, minus here, minus iota h ket upon twice m del square psi star upon, sorry, del x square, sorry, what it was, del square psi star upon del x square, and then you have a psi here as well. So I'll place a psi here as well. Then plus iota upon h ket, you have this v star now, and then psi mod whole square. One has to understand that when I was talking about conservation of probability, one should be very much clear that I was taking V to be real. Okay. But what happens if V is not real? what happens if V contains some imaginary part as well. Okay, so if V contains imaginary part, now no longer your probability remains conserved. Okay, this is what we are trying to establish here. Okay, do understand my point. So as you're aware that this particular thing, so I'll put them together, don't worry. So it will be like iota h cat upon twice m. Then you have the psi star. I don't know how to make it in a better fashion. And then you have minus of okay. And then you have this, I'll write this iota upon h cat, and then I'll write psi mod whole square. And now you have this V star minus of V. And do remember, now no longer your V is real. So I cannot write it as 0. Earlier, I could have written it as 0 and things were very easy for us. Now, no longer it remains to be the case. So please do remember, this may be asked in your exam or probably interview anywhere. So understand my point. What if I try to find d by dt of minus infinite to plus infinite psi mod whole square dx, it is equivalent to minus infinite to plus infinite del by del t of psi mod whole square dx. So I'll write it in I'll write this as probability. So I'll write d by dt of t as a function of time is equal to what? Is equal to integrating this. So I know that if I integrate this, so in just a few minutes back, I found that if I integrate this thing, I'll get a 0. This is something that I know. If I integrate this from minus infinity to plus infinity, this is something that I'll get 0. If you remember this is something that we have done. What remains to be seen is this. So what you will get additionally, you will get minus infinite to plus infinite iota upon h cat psi mod whole square V star minus V. Is that clear or not clear? Yes or no? This is something that you're going to get. Good.
Yes, sir.
And after all, what is your V star? Now, no, as I told you, now no longer your V is not a real number. V belongs to a complex. V is a complex function. And if this is the case, then I'll write it will be V naught minus iota gamma. This is what I have given this notation as. And if I use this up, what am I going to get? I'm going to get
प्लस 2i गामा
हाँ जी सॉरी
मतलब सर वो v स्टार माइनस v होगा माइनस 2i गामा
हाँ sorry. So what I'll get? I will get what we say. I'll get iota upon h cat. अच्छा, this psi mod whole square remains into the bracket and ये हो जाएगा तुम्हारा 2 iota gamma और ये हो जाएगा minus infinite to plus infinite psi mod whole square dx, right? Is that clear? यही होगा ना? So now, if you see that d by dt of your probability as a function of time is equals to this iota will become minus 2 gamma upon h cat, and then this particular fellow is what? This is again probability as a function of time. Now, if you just find this, you'll find that this is dp t upon pt here, and you take a variable separable, you'll get minus gamma upon h cat, and this is dt. And if you integrate this thing, so you'll get some constant. Let us say I integrated from time t equal to 0 to some later time t. So I'll get p as a function of time is equal to p0, and I think exponential minus of 2 gamma h cat. Is that clear? You can integrate. This will be log. You take that log here, so you take a e here. Is that clear? I mean, if you integrate this, it's very, I'll write it here. So if I integrate, I'll get log of pt is equals to minus 2 gamma upon h cat times t. You take e here and you take some constant, and let's say that constant, I know somehow, let's say it is at time t equal to 0. Let's say time t equal to 0 probability I know. So this will represent you some constant. I'm writing it as p0. So now if I use my v, if V is complex, then probability no longer remains conserved. Rather, it becomes a function of time. Is that clear or not? So please do remember, in the cases of unstable particles, or let's say in the case where your potential in general is a complex valued function, the probability is not going to remain conserved. So whenever one asks you that whether or not the probability remains conserved, you should see what is the nature of the potential. If potential is real, indeed the probability would remain conserved. Otherwise, it will be in general a function of time. I hope I'm making sense. Is that clear?